Mathematical beauty describes the notion that some mathematicians may derive aesthetic pleasure from their work, and from mathematics in general. They express this pleasure by describing mathematics as beautiful. Mathematicians describe mathematics as an art form or, at a minimum, as a creative activity. Comparisons are often made with music and poetry. Bertrand Russell expressed his sense of mathematical beauty in these words: "Mathematics, rightly viewed, possesses not only truth, but supreme beauty, a beauty cold and austere, like that of sculpture, without appeal to any part of our weaker nature, without the gorgeous trappings of painting or music, yet sublimely pure, and capable of a stern perfection such as only the greatest art can show. The true spirit of delight, the exaltation, the sense of being more than man, which is the touchstone of the highest excellence, is to be found in mathematics as surely as poetry." Paul Erdos expressed his views on the ineffability of mathematics when he said, "Why are numbers beautiful? It's like asking why is Beethoven's Ninth Symphony beautiful? If you don't see why, someone can't tell you. I know numbers are beautiful. If they aren't beautiful, nothing is." Beauty in method. Mathematicians describe an especially pleasing method of proof as elegant. Depending on context, this may mean a proof that uses a minimum of additional assumptions or previous results, a proof that is unusually succinct, a proof that derives a result in a surprising way, a proof that is based on new and original insights, a method of proof that can be easily generalized to solve a family of similar problems. In the search for an elegant proof, mathematicians often look for different independent ways to prove a result. The first proof that is found may not be the best. The theorem for which the greatest number of different proofs have been discovered is possibly the Pythagorean theorem, with hundreds of proofs having been published. Another theorem that has been proved in many different ways is the theorem of quadratic reciprocity. Carl Friedrich Gauss alone published 8 different proofs of this theorem. Conversely, results that are logically correct but involve laborious calculations, over-elaborate methods, very conventional approaches, or that rely on a large number of particularly powerful axioms or previous results are not usually considered to be elegant, and may be called ugly or clumsy. Beauty in results. Some mathematicians see beauty in mathematical results that establish connections between two areas of mathematics that at first sight appear to be unrelated. These results are often described as deep. While it is difficult to find universal agreement on whether a result is deep, some examples are often cited. One is Euler's identity. This is a special case of Euler's formula, which the physicist Richard Feynman called our dual, and the most remarkable formula in mathematics. Modern examples include the modularity theorem, which establishes an important connection between elliptic curves and modular forms, and monstrous moonshine, which connects the monster group to modular functions via string theory, for which Richard Borchers was awarded the Fields Medal. Other examples of deep results include unexpected insights into mathematical structures. For example, Gauss's theorem or egregium is a deep theorem which relates a local phenomenon to a global phenomenon in a surprising way. In particular, the area of a triangle on a curved surface is proportional to the excess of the triangle, and the proportionality is curvature. Another example is the fundamental theorem of calculus. The opposite of deep is trivial. A trivial theorem may be a result that can be derived in an obvious and straightforward way from other known results, or which applies only to a specific set of particular objects such as the empty set. Sometimes, however, a statement of a theorem can be original enough to be considered deep, even though its proof is fairly obvious. In his A Mathematician's Apology, Hardy suggests that a beautiful proof or result possesses inevitability, unexpectedness, and economy. Rota, however, disagrees with unexpectedness as a sufficient condition for beauty and proposes a counterexample. A great many theorems of mathematics, when first published, appear to be surprising. Thus, for example, some 20 years ago, from 1977, the proof of the existence of non-equivalent differentiable structures on spheres of high dimension was thought to be surprising, but it did not occur to anyone to call such a fact beautiful, then or now. Perhaps ironically, Monastirski writes, "It is very difficult to find an analogous invention in the past to Milnor's beautiful construction of the different differential structures on the seven-dimensional sphere." The original proof of Milnor was not very constructive, but later E. Briscorn showed that these differential structures can be described in an extremely explicit and beautiful form. This disagreement illustrates both the subjective nature of mathematical beauty and its connection with mathematical results. In this case, not only the existence of exotic spheres, but also a particular realization of them. Beauty and experience. Interest in pure mathematics separate from empirical study has been part of the experience of various civilizations, including that of the ancient Greeks, who did mathematics for the beauty of it. Mathematical beauty can also be experienced outside the confines of pure mathematics. For example, the aesthetic pleasure that mathematical physicists tend to experience in Einstein's theory of general relativity has been attributed to its great mathematical beauty. Some degree of delight in the manipulation of numbers and symbols is probably required to engage in any mathematics. Given the utility of mathematics in science and engineering, it is likely that any technological society will actively cultivate these aesthetics, certainly in its philosophy of science if nowhere else. The beauty of mathematics is experienced when the physical reality objects are formulated using totally abstract mathematical models. Mathematicians develop an entire field of mathematics with no application in mind, and years later, physicists discovered that these abstract mathematical branches make sense of their observations. For example, the group theory, developed in the early 1800s for the sole purpose of solving polynomial equations, turned out to be the most fruitful way of categorizing elementary particles, the building blocks of matter. Similarly, the study of knots, which mathematicians analyzed purely as an esoteric arm of mathematics, provides important insights into string theory and loop quantum gravity. The most intense experience of mathematical beauty for most mathematicians comes from actively engaging in mathematics. It is very difficult to enjoy or appreciate mathematics in a purely passive way. In mathematics, there is no real analogy of the role of the spectator, audience, or viewer. Bertrand Russell referred to the austere beauty of mathematics, beauty and philosophy. Some mathematicians are of the opinion that the doing of mathematics is closer to discovery than invention. For example, there is no scientific discoverer, no poet, no painter, no musician, who will not tell you that he found ready-made his discovery or poem or picture, that it came to him from outside, and that he did not consciously create it from within. William Kingdon Clifford, from a lecture to the Royal Institution titled, "Some of the Conditions of Mental Development." These mathematicians believe that the detailed and precise results of mathematics may be reasonably taken to be true without any dependence on the universe in which we live. For example, they would argue that the theory of the natural numbers is fundamentally valid, in a way that does not require any specific context. Some mathematicians have extrapolated this viewpoint that mathematical beauty is truth further, in some cases becoming mysticism. Pythagorean mathematicians believed in the literal reality of numbers. The discovery of the existence of irrational numbers was a shock to them, since they considered the existence of numbers not expressible as the ratio of two natural numbers to be a flaw in nature. From a modern perspective, their mystical approach to numbers may be viewed as numerology. In Plato's philosophy there were two worlds, the physical one in which we live and another abstract world which contained unchanging truth, including mathematics. He believed that the physical world was a mere reflection of the more perfect abstract world, Hungarian mathematician Paul Erdos spoke of an imaginary book, in which God has written down all the most beautiful mathematical proofs. When Erdos wanted to express particular appreciation of a proof, he would exclaim, "This one's from the book." This viewpoint expresses the idea that mathematics, as the intrinsically true foundation on which the laws of our universe are built, is a natural candidate for what has been personified as God by different religious believers. 20th-century French philosopher Alain Badiou claims that ontology is mathematics. Badiou also believes in deep connections between mathematics, poetry and philosophy. In some cases, natural philosophers and other scientists who have made extensive use of mathematics have made leaps of inference between beauty and physical truth, in ways that turned out to be erroneous. For example, at one stage in his life, Johannes Kepler believed that the proportions of the orbits of the then-known planets in the solar system have been arranged by God to correspond to a concentric arrangement of the 5 platonic solids, each orbit lying on the circumsphere of one polyhedron and the insphere of another. As there are exactly 5 platonic solids, Kepler's hypothesis could only accommodate 6 planetary orbits and was disproved by the subsequent discovery of Uranus. Beauty and mathematical information theory. In the 1970s, Abraham Moles and Frieda Nake analyzed links between beauty, information processing, and information theory. In the 1990s, Jürgen Schmidhuber formulated a mathematical theory of observer-dependent subjective beauty, based on algorithmic information theory. The most beautiful objects among subjectively comparable objects have short algorithmic descriptions relative to what the observer already knows. Schmidhuber explicitly distinguishes between beautiful and interesting. The latter corresponds to the first derivative of subjectively perceived beauty. The observer continually tries to improve the predictability and compressibility of the observations by discovering regularities such as repetitions, and symmetries and fractal self-similarity. Whenever the observer's learning process leads to improved data compression such that the observation sequence can be described by fewer bits than before, the temporary interestingness of the data corresponds to the compression progress, and is proportional to the observer's internal curiosity. Reward mathematics and the arts. Music. Examples of the use of mathematics in music include the stochastic music of János Zenárs, counterpoint of Johann Sebastian Bach, polyrhythmic structures, the metric modulation of Elliott Carter, permutation theory and serialism beginning with Arnold Schoenberg, and application of shepherd tones in Karlheinz Stockhausen's Hymnen. Visual arts. Examples of the use of mathematics in the visual arts include applications of chaos theory and fractal geometry to computer-generated art. Symmetry. Studies of Leonardo da Vinci, projective geometries in development of the perspective theory of Renaissance art, grids in op art, optical geometry in the camera obscura of Giambattista della Porta, and multiple perspective in analytic cubism and futurism. The Dutch graphic designer M.C. Escher created mathematically inspired woodcuts, lithographs, and mezzotints. These feature impossible constructions, explorations of infinity, architecture, visual paradoxes and tessellations. British constructionist artist John Ernest created reliefs and paintings inspired by group theory. A number of other British artists of the constructionist and systems schools also draw on mathematics models and structures as a source of inspiration, including Anthony Hill and Peter Lowe. Computer-generated art is based on mathematical algorithms.